What if I told you that a single idea completely changed artificial intelligence? An idea that powers ChatGPT, Gemini, Claude, and almost every modern AI system today. But why was it needed? What was wrong with the architecture that came before it? And how did it spark the AI revolution we are witnessing right now? This is the story of Transformers. Today, AI can write code, create images, and hold remarkably human conversations. Powering many of these breakthroughs is a single architecture, the transformer. It became the foundation of many LLMs we are using today itself. But to understand why it changed everything, we first need to understand the problem it was built to solve. For decades, researchers searched for better ways to teach computer language. Rule-based systems were rigid; statistical models learned patterns from data, and neural networks brought major improvements. Yet one challenge remained stubbornly difficult: understanding meaning from context. Look carefully at the two sentences on screen. I went to the bank to deposit money. I sat on the river bank. The word bank appears in both sentences, yet the meaning is completely different. In the first sentence, bank refers to a financial institution. In the second sentence, it refers to the edge of a river. As humans, we don't even think about this. Our brains automatically use surrounding words to determine meaning. For machines, however, this turns out to be surprisingly difficult, and solving this problem became one of the biggest goals in natural language processing. To process language as a sequence, researchers introduced recurrent neural networks, or RNNs. Instead of reading an entire sentence at once, an RNN processes words one by one, carrying information forward through an internal memory called the hidden state. The idea was simple. If the network remembers previous words, it should understand context better. And for a while, it worked. RNNs were a major breakthrough in language processing, but they came with several limitations. As sentences became longer, they often forgot important information from earlier words. Because words had to be processed sequentially, they couldn't fully utilize parallel computation, and as a result, training became increasingly slow on long pieces of text. These limitations eventually pushed researchers to look for a better solution. Imagine the model is reading a very long sentence. It encounters the word animal near the beginning. Many words later, it reaches the word it. To understand what it refers to, the model must remember animal. The problem is that information has to travel through many processing steps before it reaches the end. As it travels, the signal becomes weaker and weaker. Eventually, important information starts fading away. That's exactly what you are seeing on screen. The earlier words lose their influence. The challenge became known as the vanishing gradient problem, and it prevented RNNs from understanding long-range relationships effectively. Researchers needed a smart memory system. That's where long short-term memory, or LSTMs, came in. Think of these gates as intelligent filters. The forget gate decides what information should be discarded. The input gate decides what new information should be stored. And the output gate decides what information should move forward. Suppose the model is reading a story about a cat. The LSTM can learn to keep important information about the cat while discarding irrelevant details. This significantly improved memory retention. For years, LSTMs became the dominant architecture in language processing, but they still carried a major limitation inherited from RNNs. As you can see, word 1 must be processed before word 2, word 2 before word 3, and so on. No matter how powerful your hardware becomes, you are forced to wait. That's a huge problem. Modern GPUs are designed to platform thousands of computations simultaneously, but RNNs and LSTMs cannot take full advantage of that power. Training became slower, scaling became harder, and handling very long contexts remains challenging. Researchers needed a completely different approach, not a better RNN, something entirely new. This is where one of the most important ideas in AI history appears: attention. Look at the connections forming between the words. Instead of passing information through a long chain, every word can directly examine every other word. If we are processing the word sat, the model can immediately look at cat. It doesn't need to travel through multiple intermediate steps. The model learns which words matter most for understanding each token. In simple words, it learns where to focus its attention. And unlike RNNs, it can do this for all words simultaneously. In 2017, researchers at Google published a paper with a remarkably bold title. Attention is all you need. Their proposal was radical. Remove recurrence entirely. Remove LSTMs. Remove sequential processing. Keep only attention. The results shocked the AI community. The new architecture trained faster, scaled better, and achieved state-of-the-art performance. That architecture became known as the transformer. And from that moment onward, AI entered a completely new era, the transformer architecture. Now let's look at the big picture. Input text enters the system. Those words became embeddings. Positional information is added. The encoder processes the sequence. The decoder generates outputs. Finally, probabilities are produced and the next word is selected. At first glance, this may seem complicated, but every component exists for a specific reason, and by understanding them one by one, the entire architecture becomes surprisingly intuitive. Computers don't understand words, they understand numbers. So before a transformer can process language, every word must be converted into vector. That's what embeddings do. Notice how words become list of numbers. Those numbers capture meaning. For example, cat and dog often end up close together in vector space because they are semantically related. Meanwhile, a word like run may appear somewhere else. The transformer doesn't see text, it sees landscape of numerical relationships. Embeddings are the bridge between language and mathematics. There's a problem. Transformers process all words at the same time. That's great for speed, but how does the model know which word came first? Look at the positions on screen. Position 1, 2, 3. Additional information is added to every embedding so the model knows where each word appears. Without positional encoding, these two sentences would look identical. The dog chased the cat chased the dog. Clearly, they mean different things. Position helps the transformer preserve word order. Now we arrive at the heart of transformer, that is self-attention. Look at the attention lines connecting the words. Suppose we are processing the word mat in the sentence. The cat sat on the mat. The model can immediately look at cat. It can look at sat. It can look at every word in the sentence. Some connections receive more importance than others. That's exactly what these attention weights represent. Instead of treating every word equally, the model learns which words matter most for understanding a particular token. So, how does attention actually work? Every word creates three vectors: a query, a key, and a value. Imagine searching for information in a library. The query is what you are looking for. The keys are labels attached to books. The values are the actual contents of those books. The query compares itself against every key. The stronger the match, the more attention that value receives. This simple mechanism allows the transformer to dynamically gather relevant information from the entire sentence. Let's follow the process step by step. First, queries and keys are compared. This produces similarity scores. Higher scores mean stronger relationships. Next, those scores are converted into attention weights. Finally, the attentions are applied to the values. The result is a new representation that contains information from across the entire sequence. What makes this remarkable is that every token performs this calculation simultaneously. That's one of the biggest reasons transformers scale so effectively. But the transformer doesn't stop at one attention mechanism. It uses many. This is called multi-head attention. Think of each head as a different specialist. One head may focus on grammar, another may focus on subjects and objects, another may track long distance relationships, another may capture semantic meaning. All these perspectives are computed in parallel, then combined together. Instead of looking at language through one lens, the transformer looks through many, and that dramatically improves understanding. The real transformer doesn't use just one encoder layer and one decoder layer. It stacks many of them. Each layer refines the information produced by the previous one. of it like repeatedly polishing a rough sketch. The first layers capture basic relationships. Higher layers discover increasingly complex patterns. By the time information reaches the top, the model has built a rich understanding of the entire sequence. That's one reason transformers can perform such sophisticated tasks. So, how does a transformer actually learn? At its core, the task is surprisingly simple. Predict the next token. Suppose the input is the sky is or I love. The model generate probabilities. For sentence like the sky is, the probabilities may be blue, maybe bright, maybe cloudy. The correct answer receives the highest reward. Errors are calculated, weights are updated, and this process repeats billions of times across enormous datasets. Over the trans over time, the transformer learns language, facts, patterns, reasoning strategies, and surprisingly complex behaviors. After 2017, progress accelerated at an extraordinary pace. GPT-1 showed the potential of large-scale language model. GPT-2 shocked people with coherent text generation. GPT-3 demonstrated the power of scale. Then came Dolly, ChatGPT, GPT-4, Claude, Gemini, and many more. Nearly every major AI breakthrough of the modern era traces back to the same foundational architecture, the transformer. Let's bring everything together. RNNs introduced sequential processing, LSTMs improved memory, attention solved long-range dependencies, and transformers combined attention with massive parallelism. The result was faster training, better context understanding, and the foundation of modern AI. Today, nearly every major language model, from GPT to Gemini and Claude and beyond, builds upon these ideas. And that's the story of Transformers, the architecture that didn't just improve AI, but redefined what AI could become. If you enjoyed this video, don't forget to like, subscribe, and I'll see you in the next one.